Okay, so good afternoon to everyone. First of all, let me thank you for coming. This is the first colloquium, actually, of the new year, 2026. And we welcome Professor Alberto Sesana from the University of Milano-Bicocca. As usual, before the colloquium, just 2 words of introduction. Professor Sesana is full professor in astrophysics. His main research field is in the gravitational wave research, in particular in the context of aspects of gravitational wave astrophysics, massive black hole binaries, and which actually will be in particular the topic of the colloquium, pulsars as cosmic, let's say, observatories for the detection of gravitational waves. Is, as you can see, indeed a member of different gravitational wave collaborations, international. The European Pulsar Timing Arrays, the International Pulsar Timing Arrays, and actually is also a member of the LISA satellite collaboration. Just let me remind you and recall you also that before joining the University of Milano, he held actually different research positions all around the world, in Germany, at Potsdam, at the Albert Einstein Institute, the University of Birmingham in UK, and also actually the Pennsylvania State University in the USA. And let me also recall that actually he's the recipient of different awards and grants, actually 2 ERC grants, one a consolidator and an advanced grant. So today we'll tell us about another actually milestone, we could say, in gravitational wave research, actually the first ever detection of a stochastic gravitational wave background, which was detected 2 years ago, 2023, at the nano-Hz frequencies, and which actually is really another breakthrough, I would say, in gravitational wave research, but in physics in general, I would say, and with a lot of consequences for astrophysics and astronomy and cosmology. So I leave the word to our speaker. Thanks a lot. Thank you.
Thank you. Thank you very much. Va? Si sente? No? Si? Good? I'm on? Okay. Thanks, Nicola, for the very nice introduction, and thanks for the invitation. It's really, you know, almost, it's a very nice auditorium. It's not very often you do a colloquium in front of so many people, and I see a lot of young faces, which is always good. Are there a lot of students in this room? Put your hands up. Okay, right. So you're all students of physics, though, right? Okay. Now, just to gauge a little bit what I'm going to say. All right. So today I will talk about gravitational waves, all right, which is this new, well, relatively new way to explore and understand the universe. And in particular, I will focus, as was said in the introduction, on a technique for detecting gravitational wave at very low frequencies. So we're talking about frequency of the nano-Hz by timing millisecond pulsars, okay? So this is the very rough outline of my talk. So I will talk a little bit about how we use pulsars to detect gravitational waves. I will talk a little bit about the primary sources of gravitational wave that we expect at nano-Hz frequency, in particular astrophysical sources or massive black hole binaries. And then I will show you the results that we had a couple of years ago and what they mean, what are the implications, and where we move from here. All right, so a little bit on gravitational waves, right? So you're all familiar with the electromagnetic spectrum. So this is a chart of all the missions by ESA that probe different bands of the electromagnetic spectrum. And you all know that it's important to cover all this band because by seeing the universe at different wavelengths, you learn different things, right? So this is just a collection of pretty pictures, but no, you all know, for example, in the bottom right there, that if you look at the galaxy at different wavelengths, you see different phenomena, right? So covering the electromagnetic spectrum is important. It's just seeing the universe with different eyes, right? Now, gravitational waves add another layer of understanding, of knowledge of the universe, of sensing the universe, by adding essentially the hearing, okay? It's not like seeing the universe, it's like listening to the universe. And the same way there is an electromagnetic spectrum, there is a gravitational wave spectrum. Gravitational waves are, I will tell a little bit about that, are waves that propagate at the speed of light, pretty much like electromagnetic waves, right? And they cover a very large frequency range that goes from kilohertz, right? So which is essentially the audio band, right? And you probably all of you have heard some LIGO Virgo detection, put in an empty MP3 file with the whoop, right? Down to essentially the inverse of the age of the universe. And of course, as physicists, astrophysicists, cosmologists, we want to probe all, these different windows, this range, and we have different observational windows. Now, listening to gravitational waves, observing gravitational waves is particularly complicated, and in fact, it took several years since they were predicted in 1916 to the first detection, which happened pretty much 100 years later, right? And the primary sources of gravitational waves are binaries of compact objects. Binaries in spiral around each other, the two objects of the binary, they distort the fabric of space-time, and this distortion propagates outwards as a wave. And it's the space-time itself that contracts and expands. So it's pretty much like you steer your finger in a pond and you see the waves going to the pond, right? It's similar, okay? So binaries, compact binaries, are the main sources of gravitational waves. And this is, the landscape of those binaries before 2015, right? So you see mass on the x-axis, redshift on the y-axis, or cosmological distance. Essentially, this is just a blank plot, right? We didn't have anything. And then, of course, LIGO Virgo came, and they started to observe black hole binaries in the local universe. We learned a lot about how this system form, what is their mass function, and so on and so forth. And by now, well, this is O3 still, but with O4, we have more than 200 detections. But still, those are stellar mass black holes in the relatively nearby universe, right? So we are really just starting to pierce into the very low mass and local portion of the parameter space here. So this is what we can do with ground-based interferometers now that cover essentially the high frequency band, okay? Now, there is another band that we have access to right now, but it's with a very different technique. So we do not build an instrument from scratch like a laser interferometer, but we make use of astronomical objects that nature provided to us. And this technique is the timing of millisecond pulsars, okay? So I'm gonna spend a little, the first part of this talk by explaining a little bit how this technique works. So essentially, you all know what a pulsar is. A pulsar is a rotating neutron star that emits radio beams, right? And they are essentially cosmic lighthouses, okay? And since they have a mass which is pretty much the mass of the sun and a radius of 10 kilometers, and they spin very quickly, they have a huge moment of inertia, so it's very hard to change their rotation. So they are essentially very precise cosmic clocks. And if you have a very precise cosmic clock, what you do, you time this clock. You record the time of arrival of the pulsations. okay? And this is what you do in pulsar timing. So you have a clock that you have a spinning body, you model your clock, and you construct a physical model to predict each time of arrival of your clock, okay? What you do, you construct a timing model of your pulsar. And it's a relatively complicated thing to do because, pulsars are not perfect clock, they spin down, so you have to consider the spin down, the nu dot, nu double dot of the pulsar, and you have to consider all sort of relativistic astrophysical effect and propagation effect and so on and so forth. Or even Keplerian effect. Most of these pulsars are in binaries, so you have to fit for the binary motion of the pulsar to construct your timing model, okay? But the idea is that when you construct a deterministic timing model for this pulsar, what you can do, you can compare the actual time of arrival of the pulses on the top here to the time of arrival that are predicted by your model, right? You can fit for the best parameters and find the best solution. Now, of course, your model is not going to be perfect, and there's going to be noise in your observations, right? When you subtract the predicted time to the observer time, you end up with a residual, okay? A small mismatch between what you predicted and what you actually observed. And this residual encodes essentially noise and any physics that you might have missed in your modeling. For example, if there was a gravitational wave passing between you and the pulsar. And the idea is very simple. Just let's take this cartoon. Suppose you have, the pulsar and the Earth. The pulse propagates from the pulsar to the Earth, and there is a gravitational wave passing through. So gravitational waves are a transverse wave that stretch and squeeze space in a quadrupolar fashion, like that, right? So the space is squeezed in one direction and is stretched in the perpendicular direction in an oscillatory fashion, okay? So the idea is that if you have a gravitational wave that comes between you and the pulsar, the stretch and squeeze of space makes the pulsar recede from you or approaching you periodically, right? So your next time of arrival, your next pulse will arrive a little bit earlier or a little bit later than predicted, depending on the phase of the wave. So if you plot the residuals, instead of having just flat white noise, a white spectrum, what you have, you can see like the sinusoidal behavior of the wave, because you didn't take that into account in your modeling, okay? So this is the key idea. You used your clock to detect the delays induced by the propagation of gravitational waves. Now, if you want to, so this is the technique, and you want to understand what kind of sources you can detect with this technique. And if you do some math, essentially you find out that this residual, this timing residual, is of the order of the amplitude of the strain of the wave, which is the relative change in the metric, right? The relative expansion and contraction of space, divided by the frequency. And if you plug in numbers, you find that these residuals are of the order of tens or hundreds of nanoseconds, okay, if the source of your gravitational wave is a supermassive black hole binary of 1 billion solar mass at a cosmological distance of like hundreds of megaparsecs. So not very, in the local universe. But the point is that a residual of hundreds of nanoseconds is something that we can measure in pulsar timing with current telescopes. Okay, so it's not hopeless, that's the thing. All right, so what we are doing, we are timing pulsars for decades, and of course we don't have the capability to look at to stare at each pulsar all the time. We use big radio telescopes, and we time one pulsar today, and then another day, and then we go back to the pulsar maybe 2 weeks later. So the frequency range to which we are sensitive is essentially the inverse of our experiment length, so let's say 1 over a decade as a minimum frequency, and the maximum frequency is essentially dictated by the interval between observations. And this poses the frequency band of PTA in the nano-Hz range. It goes from nano-Hz to micro-Hz at best. So here is the gravitational wave landscape. You have frequency on the x-axis and characteristic strain, the typical oscillation of space, the amplitude of the oscillation of space on the y-axis. And you see different probes and different sources on this chart here. Okay, at kilohertz, high frequency, you see the ground-based detectors and the in-spiral of black hole binaries that produce gravitational waves and the frequency there. Pulsar timing is a very low frequency. It's at the opposite end of the spectrum. And you can see there, you can detect things up to 10 to the minus 15, 10 to the minus 14 in strain. And the frequency range is nano-Hz to microhertz. Now, what kind of sources we expect to see there? Okay, the primary astrophysical source is the stochastic superposition of waves coming from a cosmological population of adiabatically spiraling supermassive black hole binaries. Okay? Now, our best understanding of the formation of structure in the universe right now is that it proceeds in a hierarchical fashion. Okay? Big galaxies today are produced by a lot of physical mechanisms, among which the merger of smaller units into forming bigger and bigger galaxies, okay? So what you see there at the bottom left is a movie from a cosmological simulation of galaxy formation, and you see all these, especially the left panel there, you see those are the stellar components. You see these galaxies forming, and you will see soon galaxies merging one with each other, okay? Now, we know that at the center of massive galaxies, there are supermassive black holes. So if at the center of two galaxies, there are two supermassive black holes, and these two galaxies merge, okay, the result will be the formation of a supermassive black hole binary, okay? The process of galaxy merger is quite common. If you take a picture of the sky with a Hubble Space Telescope, a large fraction of the galaxies that you see are interacting with other galaxies, and they are merging. So there's a lot of merging systems in the universe, and there's a lot of galaxies that are expected to harbor massive black hole binaries in some stage of their evolution, okay? Now, so the idea here is that if you take a picture of the sky will be filled with different massive black hole binaries with different masses at different redshifts emitting at different frequencies. So you will have a series of gravitational waves coming to you from all directions and superimposing incoherently to form a sort of confusion noise, a stochastic background, okay? Now, you can work out the math, and if you assume that your binaries shrink because of gravitational wave emission, because gravitational waves take away energy from the system and the binary shrinks, okay? And if you assume that all these binaries are circular, you will find that this superposition of sources produces a signal which has a very specific spectrum. And the theoretical spectrum goes with the frequency to the minus 2/3. This is the typical strain, the characteristic strain of the spectrum as a function of frequency, okay? So you have larger oscillations at lower frequencies. All right, but let's keep in mind this number because it's a number that creates a lot of confusion, and we'll come back later. In reality, this is not a continuum spectrum. It's the superposition of many systems emitting incoherently at many frequencies, okay? Let's keep this in mind. If you take a realization of the massive black hole binaries in the universe, and you compute the signal, you find something like this, okay? So in this plot here, you see frequency on the left axis, on the x-axis, and amplitude and the strain on the y-axis. Each triangle is the strain produced by one source. And the overall signal you see there as a green line. And where I subtract the brightest sources, you see something right, the red line. Now, you see that at very low frequency, it sort of falls onto this f to the minus 2/3 power law, which is the black line there. But at higher frequency, it tends to departure quite a bit, okay? So the fact that the signal is a power law at f to the minus 2/3 is a very, very first order oversimplification, okay? And we come back to that in a second. All right, if I take this and I inverse Fourier transform the signal and I go to time domain and I inject this signal in some pulsars, what I see is something like the red curve. So, and that's the typical shape of a red noise, right? So this is a red signal. But if I look at a typical pulsar in the sky, and I time a pulsar, I can see residuals that do something like this. So is this the signature of a gravitational wave background? Hard to tell, right? Because, of course, pulsars are very precise clocks, but we don't have them under control. We don't know exactly what they do. There are processes, there are noise sources that are inherent to the pulsars that can produce red noise, red processes that can produce red noise. So in order to be sure that what we see in a pulsar is due to gravitational waves, we cannot rely on having a clock and measuring the timing residual. We need to rely on an array of clocks. So we need to time an array of pulsars. And this is where the concept of pulsar timing arrays come about, okay? Which is depicted schematically in a cartoonish way here. So the idea is to time pulsars at different locations in the sky and to cross-correlate the time of arrival, the residuals of different pulsars. And the idea is that the correlation of the residuals from pulsars in two directions in the sky depends on the relative separation of those pulsars. And it follows a specific pattern which has an expectation value that has this shape, which was derived by Ellings and Downs in 1983. So you see the correlation is positive at low. So this is the correlation of the time of arrival of the residuals in the time of arrival as a function of the angle between the two pulsars. Okay, so 0, the two pulsars are pretty much in the same direction in the sky. 180, they are antipodal, okay? Now, the shape in itself is a bit, it's complete. So you have this positive, negative, positive kind of behavior, and the exact shape is a little bit complicated to derive, depends on the antenna pattern function, a bunch of stuff. But the basic reason why it is like that, okay, the basic feature there depends essentially on the quadrupolar nature of the gravitational waves. And it's very simple to understand when you think as a gravitational wave as something that is quadrupolar, right? Shrinking in one direction, expanding in the opposite direction. So now let's do this thought experiment. Suppose there is just one wave, okay, that is going in the screen here. So the way the space oscillates in this direction, okay, like that. The Earth is at the center there, and the pulsars are in the direction of the two red lines, okay? Now, if the pulsars are in the same direction in the sky, you see that as the space is expanding in the direction of a pulsar, it's expanding also in the direction of the other pulsar, right? So if the pulse from pulsar 1 arrives a little bit later, I expect also the pulse from pulsar 2 to arrive a little bit later. So I expect these residuals to be positively correlated. And now you understand how the game works, right? If the two pulsars are at 90 degrees with each other, you can expect the two residuals to be anti-correlated, because as space is expanding in the direction of a pulsar, it's contracting in the direction of the other pulsar. And of course, if you are at 180 degrees, again, you have positive correlation. Now, of course, this is a very simplistic view, because in reality, you have waves coming at different frequencies from all directions. And you have to average over all these things, and that's why you get this very complicated shape. But the key positive, negative, positive, depends essentially on the quadrupolar nature of the wave. So we need to time a lot of pulsars, and to time a lot of pulsars, we need a lot of telescopes. And that's why this is a, coherent, well, coherent is maybe too much. It's a semi-coherent effort of the worldwide community. There are several collaborations that are listed there on the right that use big telescopes all around the world in order to time as many pulsars as possible to correlate the best timing residuals from the most pulsars. Each collaboration works pretty much on their own data with their own telescopes, but they also share data and collaborate within the framework of the International Pulsar Timing Array. So we have this sort of two-tier collaborations, right? We do our regional things, but we also share data with other PTAs in order to produce a worldwide data set that includes the data from all the pulsar, from all the arrays. All right, so this is pretty much the framework. What we are doing, we are looking for this shape in the data, and what happened, after tens of years of timing these pulsars, we finally got to the sensitivity when we started to see something, okay? And those are the results that were published by, okay, these are two examples. On the left, we have the results from the European Pulsar Timing Array. That's, let's say, the collaboration I belong to. And on the right, the results from Nanograph. And you see for the first time a sort of first evidence of these positive, negative, positive behavior. So you see it's not spectacular in the sense that the error bars are very large. And in fact, this is a roughly 3 sigma results, okay? You have 3 chances in 1,000 that nature is fooling you, and that's just by chance. Whatever, I mean, that's what it is. So we have a tentative, let's say, quite compelling in a sense because it's not just one collaboration, right? There are several collaborations that are seeing pretty much the same pattern. Detection of these low frequency, quadrupolar behavior, which is indicative of an incoherent superposition of gravitational waves. What does it mean? Well, first of all, this is just the smoking gun, right? We want to look also at the spectrum. How does the spectrum look like? Not great, in a sense, right? Because, of course, this first detection is 2, 3, 3.5 sigma. We are just constraining very few frequency beams. So the constraint that we have is actually quite loose. And what you see there is essentially the amplitude over the slope of the power law. Now, there you see on the x-axis, on the right, you see this gamma coefficient. This gamma coefficient, which is 3 minus 2 alpha. The alpha there is the minus 2/3 in characteristic strain that I showed before. Because this is the spectrum of the residual, which is not the same thing as the spectrum of the strain, okay? Now, the f to the minus 2/3 that I showed you before, there would be the vertical line at minus 13.3 over 3, okay? So you see, well, the data lies a bit to the left of this. So they're, well, within 2 sigma is probably consistent, but it's shifted towards a flatter spectrum. And also, the amplitude of this signal is actually quite high. It's a bit higher than expected from vanilla population model of massive black hole binaries. And so that's where you find, people saying things, it's too flat to the supermassive black hole binaries, and then you can add your early universe model, favorite early universe model to fit the data. Now, I'm gonna be a little bit provocative here because I know there's a lot of cosmologists here, okay? So I want to quote my good friend, Yuri Levin, from the week after the results were published. It's like looking at the archive, I can't help wondering, is there any early universe cosmological process that does not produce the stochastic gravitational wave background observed by pulsar timing arrays? And in fact, obviously there has been a lot of fuss about this, and there has been a lot of publication just putting forward different explanations for this, right? It can be produced by some inflationary process. It can be produced by some phase transition. It can be produced by some topological defects, strings, domain walls, whatever. It's strings, it's turbulence, it's inflation, it's a bird, it's a plane. It's very likely supermassive black hole binaries, okay? Even though, I'm gonna step back on this statement, we have no observational proof yet that is supermassive black hole binaries, okay? So I'm gonna be clear here. So I think it's still very likely that this signal is produced by supermassive black hole binaries. There is no evidence really that it's not. But there isn't any smoking gun as of now that it is due to supermassive black hole binaries. So to all the cosmologists in the room, please keep working on your favorite cosmological model because, you know, it's still game, okay? Everything is still game. Now, why I'm saying that it's very likely supermassive black hole binary? Well, first of all, because when you model the signal from supermassive black hole binaries, you don't have to stop at the first order. Okay, this signal is not a smooth f to the minus 2/3 power law because of very different things. So first of all, binaries, massive black hole binaries, do not get teleported magically to the center of the galaxies and they just emit gravitational wave and evolve. They need to get there. And to get there, and they cannot get to those small separation by emitting gravitational waves because a gravitational wave emission is very inefficient at large separation. They need to get there by losing energy and angular momentum to their immediate environment, to stars and gas in the nucleus of the galaxy. So there is energy of the binary that is not lost in gravitational wave, but is lost to the environment. And this push down the spectrum at low frequency. Another thing that changes the spectrum at low frequency is eccentricity. The more eccentric is the binary, the more this gravitational wave is not emitted only at one frequency, it's emitted in a spectrum of frequency, and that also flattens the signal, okay? So, if I show you what happens for an astrophysical population of massive black hole binary, okay, this is a bit complicated, there's a lot of stuff in there, but look at the top left panel. So there you see the hundreds of realization of this signal with the expectation in black and other stuff, right? But the important thing here is that as I dial up the eccentricity of my binaries, this signal flattens at low frequency and it turns over. Now, the frequencies where we are most sensitive with PTAs are around, few nano-Hz, right? So if I have something like this, and I see like a couple of beams at few nano-Hz, I can very well say that the spectrum is flat and not f to the minus 2/3. Okay, so that's one thing. Another very important thing is that the signal is not smooth, it's not a power law, right? So these are 100 realizations of the very same population of massive black holes. Each of them is different. Each of them has some jugs, some excess power at some frequency. Okay, so it might well be that it's just because of the variance of the signal that you're measuring something that is not an f to the minus 2/3 power. So in fact, what we did, we considered a phenomenological model for the population of massive black hole binaries by including different ingredients. So we modeled the merger rate with uncertainty of galaxies with all the uncertainty that it has. We populate these galaxies with massive black hole according to the black hole galaxy relation with all the uncertainty that they have. And we produce this huge parametric model, and we use this model to do realizations of the universe to produce those type of signals. And then what we can do, we can compare the distribution of the power as a function of frequency to what we observe. And what you get is something like you have there in the left. And you see the orange one is the measured power. The green one are these hundreds of thousands of models from this realization. Now, this is not a statistical proof or anything. It's just to show you that it's very easy to get realization of the universe that goes essentially through the data. Okay? So it's quite easy to reproduce the data with an astrophysical model. Okay? Not only, you also have to consider the problems on the detection side. Don't take the detection as the truth. The detection is a 2, 3, 3.5 sigma. And it has all the problems of a 2, 3, 3.5 sigma detection. Example, look at the bottom left panel here. In the bottom left panel, we injected a smooth power law, which is f to the minus 2/3, which is exactly where the point there is, right? we run our machinery on an array that is exactly a copy, a carbon copy of the European pulsar timing array. We did several realizations of this, and at times we found something like that. F to the minus 2/3 power law, perfect, injected, recovery, offset, okay? It can't just be by chance. It can't just be due to the specific realization of the noise. I want to go a bit farther on this. European pulsar timing array data. Some of you maybe have read the paper. We have different data sets there. And we received a lot of shit, can I say shit? Criticism for that, right? Because we have a long data, because we didn't want to hide anything, right? We have a long data set, and we have a short data set, a cut of a short data set, right? And we have higher significance in the short data set than in the long one. And then all the physics 1, data analysis, statistics, they say, oh, that's impossible, right? You cannot add data and get a lower significance. You can, right? Because your data that you add, the significance that you get, if there is no extra information in the data that you add, the significance that you get is subjected to what the noise does in those data. And if the noise is bad with you, it can decrease significantly your significance. Because the noise is stochastic, right? So the statement that you cannot add data and lose significance is true on average, but it's not true in a specific realization of the universe. And in fact, we did this very nice experiment on controlled simulated data, again, exactly equal to EPTA, long data set, short data set, analyze the data with the pipeline that we used, and there are instances where we find lower significance in the longer data set. Why? Because the longer data set, as you see there at the top, in the top panel there, what you see there, that's the distribution of the residuals as a function of the frequency of the radio frequency that we are observing. So as you can see on the left of the red line, essentially we have only single frequency data. So with single frequency data, we cannot model the dispersion in the interstellar medium. And that essentially makes those data useless for gravitational wave purposes. But still, it has all the noise sources that you're trying to, beat, okay? So when you produce data sets that are like that, right, when you add to very good data that are multiband data, a long tail of data that have only one frequency, right, there are cases where you decrease your significance because your signal gets swamped by the noise in those data that you have added. And this, I'm not inventing this. This happened. We did 100 realization. In 30% of the realization, we got lower significance. Okay? So also this, I'm not saying that this is what's happening in the EPTA data. I'm just saying that this thing can happen in the EPTA data, okay? So you don't need to find necessarily any weird explanation, okay? All right, so what do we get from this detection, though? Well, we can run this detection through astrophysical modeling of the massive black hole binary population and get some posterior on some parameters. Now, as you can see, you don't even need to know what this is, right? It's just very much unconstrained. So what do we learn? Let me zoom in a few interesting things. We learn a couple of things. So first of all, these two parameters are, the T0 is the typical time after which two black holes merge after a galaxy merge, after two galaxies merge. And M star is the normalization of the M black hole galaxy relation. Okay? So what does the detection tell us? Well, the detection tells us that black holes do merge. T0 tends to be small. Okay? And that the typical massive black hole in a galaxy, the correlation between the galaxy mass and the massive black hole mass tends to be at the higher end, right? So here, by the way, sorry, green is the prior and black is the posterior. Since you are observing a signal that is a bit higher than what you expect, you favor black holes that merge efficiently and they are massive. Pretty much simple, okay? So the fact that it's flat, does it tell you anything? A little bit. So these are two parameters that are the eccentricity, and the parameter on the y-axis is essentially characterizes the environment of these binaries. So if the parameter is high, the environment is dense and the signal is flatter. So you see there is a sort of preference for the corner there. But when you look at the marginalized posterior, the evidence is scarce, right? So somehow you have some tentative evidence that these binaries are either eccentric or they evolve in a very dense environment. But essentially, this is totally inconclusive, okay? All right. Now, let me just jump ahead a little bit and talk about the elephant in the room here. So, okay, the signal can be massive black hole binaries. If it's massive black hole binaries, it tells us something about their population, okay? They tend to be massive and they tend to merge quickly. But are they massive black hole binaries? We have no evidence yet, right? And going forward, this is going to be one of the main tasks for PTA observation and analysis. So what we want to do, we want to distinguish between a signal that is due from a cosmological population of astrophysical sources from a signal that comes from some process in the early universe, because there are processes in the early universe that can produce signals like this, okay? And what are the differences? Well, of course, if you have a process that occurs in the early universe, it's much more likely to be isotropic, stationary, Gaussian, right? Compared to a signal that depends from very massive systems, okay, that are in the relatively nearby universe. And now, of course, you know that the CMB is not perfectly isotropic, et cetera, et cetera, et cetera. But at the level that you can distinguish with PTA, a cosmological signal is very likely going to be completely isotropic, Gaussian, and stationary, okay? So you want to see things like significant departure from a smooth spectrum, first of all, right? So again, this signal is going to have also a smooth spectrum, a signal that is cosmological, whereas we saw before that if you have binaries, you might have, particularly massive nearby sources that make these jags in the signal, okay? So detecting a spectrum that is clearly not smooth is an indication that this probably is due to an astrophysical population. Of course, you want to detect anisotropy. You want to detect dark spots in the sky. You want to detect non-stationarity. All these things are going to favor an astrophysical origin of the signal. However, at the moment, the data do not offer the possibility to test this. We just get upper limits, okay? And by the way, we just get upper limits that are comfortably within what you would expect from a massive black hole binary population. So it's not the fact that we don't detect this thing means that those are not binaries, okay? So we cannot tell. There can be several processes in the early universe that can produce gravitational waves at the level that we observe there. And there is a nice review that I wrote with Danny Figueroa. Of course, he wrote the part on cosmology because I know nearly zero about that. I took care of the astrophysics part. But I mean, there can be several processes. So for example, inflation. Inflation can produce this signal, but you need a tilt that is much bigger than 1 in general. So it's kind of, for what my friends tell me, this is not a very natural type of inflation. So, okay, yes, you can produce this signal, but you have to stretch a little bit things. Strings, of course, cosmic strings can do everything, right? So, and in fact, you can assume that those are strings, and you can produce some constraint on the string tension, and that's what you get from the data. You can have some first-order QCD phase transition. We tested, and other people tested this thing. But again, there are portions in the parameter space that can produce this signal, but then you have to assume that essentially almost all the energy of the universe is in magnetic energy to produce this type of signal, so which is a bit of a stretch as well. You can have things like curvature perturbation. So these are scalar perturbation in the early universe that can source gravitational wave at second order. Okay, so these are the perturbations that produce the primordial black holes. Okay, as a side effect, they also produce gravitational wave at second order. You can produce the signal with those again, but you're probing a different scale compared to the CMB, and you see the constraint on the CMB are down there, and what you would need to produce the signal that we see in PTA is up there. So you need some, something that boosts, some boosting factor at low scales to produce this signal to make it consistent with the CMB, which again, it doesn't seem to be very natural. So the bottom line here is that there are several cosmological processes that can produce this signal, but none of them really seem to be natural in a sense, okay? You always have to stretch the model a little bit. Okay, so where do we go from here? Let me just take like, some minutes to think about the future. Well, from here, the best thing that we can do always is, you always need more data. And in this case, in particular, you need better data. And to get better data, we need better telescopes. So we have now Meerkat in South Africa. It's one of the SKA pathfinders. We have FAST in China. So this is the gigantic monster of 500 meters across, which is pretty impressive. And eventually, we will have the square kilometer array, okay? And, 20 years of data with these telescopes, right, can make you go from the blue line there to the red line. And this is not insignificant because you go from marginally detecting something in 2-3 frequency beams to really characterizing the signal across a decade in frequency. And by timing more and more pulsar, you get a better sky resolution of your array, and you can actually construct a map of your signal, and you can clearly see if there are hot spots, if there are individual sources, or not, okay? So let me just give an example of what we might end up with. Suppose we are, we are looking for 30 years, sorry, you need a bit, there's a lot of students, in 30 years they're gonna still be around. Hopefully not as a student. Even though there are examples, students that playing card for 15 years in the corridors. So 30 years of observation with SKA up there, essentially, with this array, with a pulsar timing array like this, you will be able to fully characterize the spectrum, but not only, you will be able also to resolve individual sources, okay? Because if you have many pulsars, and if you have a massive black hole binaries that is emitting a gravitational wave that is particularly loud, you can actually disentangle that from the overall sea of gravitational waves that you get. And so we might be able to observe tens or maybe 30, 40 individual supermassive black hole binaries and to locate them in the sky with some precision. And now what do we do with that? Well, you want to look for some electromagnetic counterpart because you want to know where the signal comes from. Because with gravitational waves, you know from LIGO Virgo, right? You see a signal, but you don't know exactly where it comes from. And it's the same with PTA. If you see an individual source, you might say, well, it's there, okay? But there are like 1 million galaxies, okay? So you want to see some observational signature. And obviously, one thing that you might want to look at is, well, if this is an accreting binary, so those are two black holes that are accreting from a circumbinary disk, right? The accretion might be modulated over the period of the binary. And in fact, if you simulate this on a computer and you see the light curves that you produce, they seem pretty periodic. So you might want to look for periodic quasars, periodic AGN, right? The problem, though, is that the massive black hole binaries that you can resolve with PTAs are very massive and quite kind of nearby. So they are typically in elliptical galaxies that are gas poor. And in fact, if you run a model for the evolution of the universe and you try to understand what these galaxies are, the host of these massive black hole binaries are, what you see is that most of these massive black holes are quiescent. So on the top panel there on the right, you see the distribution of Eddington ratio, so how much these massive binaries are accreting compared to the Eddington limit. And there is a small blip there that is accreting relatively efficiently, right, around the Eddington, but the vast majority of them is relatively inefficient. And if you compare on the middle panel, the typical magnitude they produce in some optical band compared to the limit of, for example, LSST, you see that only perhaps 10% of them are observable. Most of them are just dark. Okay, so the problem is that observing these massive black hole binaries from their emission is going to be very challenging. However, it's probably not hopeless, because the fact that those are supermassive systems in the most massive galaxies allow you to statistically exclude a lot of galaxies in your region, error region. And this is what you see here in the top plot, right? These are all the galaxies that fall in that, sky localization there on the left panel. But if you know that you're seeing a signal with a given amplitude, from that amplitude, you know essentially what is the range of mass and distances that the binary can have. And so there, you can slice away everything that is below, essentially, everything that is black there, okay? So in the end of the day, instead of having millions of galaxies, you might concentrate your search on, well, if you're lucky, tens of galaxies. If you're unlucky, well, hundreds. But still, it's much easier to look for specific interesting features in 100 possible galaxies than in a million, okay? So the bottom line, though, here is that looking for individual binaries with PTM, even if you identify individual binaries with pulsar timing, looking for counterparts and trying to do multi-messenger astronomy, so looking at the system in gravitational waves and in the electromagnetic waves, is going to be particularly challenging. So this is really an area of open detection, it's an open area of investigation. All right, so let me just stop here. So 2023 has been a sort of new dawn in gravitational wave astronomy, right? It's the first time we detect something that is compatible with a stochastic gravitational wave signal. Let's say it's the second biggest breakthrough after the first detection of gravitational wave in gravitational wave astronomy, right? And this, but at the moment, we still don't know what this signal is. Okay, we can characterize, if we assume that these are massive black hole binaries, we can say something about the population of massive black hole binaries, but not much, because this is a very noisy 3 sigma detection. And, we are kind of now opening the opposite end of the parameter space of binaries in the universe that we can see with gravitational waves. Of course, in future, ground-based detectors will allow us to see low-mass binaries even more. LISA, I didn't talk about LISA, laser interferometers and phased antenna, is going to pretty much cover most of this parameter space, right? But with pulsar timing array, we are really cracking into the most massive, supermassive black hole binaries in the universe. Now, let me just leave you with this photo here. So this pic was taken by someone. Was taken during the European Pulsar Timing Array meeting. We were in the cupola of the Brera Observatory in Milan. And this was like 3 months before the papers that announced that this evidence came out. So this I just wanted to show, especially because there's a lot of students here, I wanted to show the collaboration. I mean, this is essentially 80% of the collaboration. So it's not LIGO Virgo, it's not CERN. We're not thousands of people, okay? So we are maybe 70, 80 people working in the European Pulsar Timing Array. And you see that most of them look like you. These are really results that were put together that from, master thesis, PhD thesis, and even researchers at the very, very start they made a significant contribution to something that is one of the biggest results in astrophysics of this decade. So really, for all the students here, keep it up because you don't need to be 30 years in the field to do a significant contribution. And I will stop there and take questions. Thank you.
Thank you. Thank you. Can you hear me? Yeah. Thank you very much for this very clear talk. So questions, especially from young students. Don't be shy.
Se fate pure gli shy dopo.
Okay. You are not young, but...
Not a young student.
Okay, thanks a lot for very interesting seminar. And you said clearly that there are no evidence of a supermassive black hole. Of course, binary, okay. It is pretty clear, I mean, the significance of this research that made on, let's say, a wide population of something that you may say, okay. You said something which is very important. Let's look to the other wavelength or other messengers, and I would like to put the question another way. Let's suppose I have a candidate of supermassive black hole,
sure.
Binary. I can tell you the direction, the periodicity, yeah. It is 2 years, and so on and so forth. Can be done, let's say, dedicated analysis. How can this can be cast? I mean, we go to previous data, or we have to take campaigns that, of course, will last, as you said, years, because if the periodicity is 2 years, I mean, so can be dedicated on the other way around instead of look to the.
Yep.
Okay, I think
sure.
You understood the question.
The question is clear.
Then I will tell you which is the source.
Okay.
Probably you know already. Okay.
So there's of course a lot of candidates in the literature, and many of those have actually been searched in PTA data. So the way a targeted search can help is by narrowing your prior, right? So if you know that there is if you can say, okay, somebody tells you, look, there might be a signal that has this frequency there, then of course you can cut a lot your prior in your search. And that, of course, for those of you that know a little bit of data analysis, in a frequentist way cuts down your trial factor, meaning that essentially you can go much, much deeper in the noise to get the same significance. No, so that has been done for many sources. For example, several of the candidates in the Catalina catalog have been searched. A few things like, well, a famous one is C366, or also OJ27, 287, and others.
G1553?
I think PG1553
this is seen in gamma rays very well.
Yeah, no, I know
it
the
is
source,
close by, and I mean, there are papers, of course. This is not
So the problem there is that most of those sources are still below the sensitivity level that we have. Actually, it's not even a problem of the sensitivity level. The problem is that in order to stick out from the stochastic background, a massive black hole binaries have to be very massive and very nearby. Most of these candidates, maybe they are, 10 to the 9 at redshift 0.5. That's not even enough to stick out of the background.
Periodicity doesn't mean that they are close by. There might be some, let's say, occultation.
Sure, can be. But this is something that is done.
Okay.
Targeted searches for candidates. Yeah.
Then, since I have the microphone, I'm curious. In your data taking, so it is made short integration in spots, or you prefer longer integration to have a better time resolution? Just Yes, to take, let's say, the pulsar data.
Right. So usually each observation is taken. Okay, it depends on the telescope, but in general, each pulsar is integrated for about 30 minutes. So data are folded for about 30 minutes in order to obtain an ISNR profile. Then you can match against the template to measure the residual. Yeah. So that's the way it's done. If you have a very powerful telescope like Meerkat, you can do that in 4 minutes.
I see.
But in general, with the other ones, it's about 15 minutes to an hour, depending on the telescope.
Okay. Thank you very much.
Studente. Grande. Nome?
Filippo.
Hi, Filippo.
Thank you for the presentation. I have a question on a specific thing you said before. So when we are analyzing for, when we have to search for the result of the Elling-Down curve, we have to do two major assumptions, and are isotropy of the source. So in general, yes, and general isotropy in the sky.
Yes.
And we have to do the assumption that the polarization is circular.
Mm-hmm.
So we do both things in general, but let's just say that we just think of a circularly polarized source that is not in general isotropic. You said before that a cosmological source would be more isotropic than the yes, the astrophysical one. So in general, if we add more data and more clearer data in the future, we would expect in both cases that the data doesn't fit the curve. And following this question, if the source is astrophysical, we would expect a more evident non-fitting of the curve.
Right. So that's a very, very, very good question. So the Ellings and Downs, it's very subtle because it's the expectation value of the correlation, and it is done with a double average. Okay. So the double average meaning that what you're doing, you are averaging over all directions in the sky of the signal, of the incoming signal, but that's a curve that is a function of the relative separation of the pulsar, right? So in reality, to grow, the expectation value is also averaged over all the possible orientation of two pulsars that have the same angle, right? So what it turns out is that even if you have an individual source, so very localized source, so not isotropic at all, right? By averaging over the direction of the pulsars, you still have that the expectation values is Ellings and Downs. What is different is the variance around the Ellings and Downs, okay? So the more anisotropic is your signal, the larger is the variance around the Ellings and Downs. So in the end of the day, if you have, suppose you have an infinite, well, very large population of pulsars. So by the way, with 30 years of the square kilometer array together with the pulsars that FAST is finding in the northern hemisphere, we might expect to put together a pulsar timing array with hundreds of pulsars, maybe thousands of pulsars in 30 years, who knows? So suppose you have a lot of pulsars, right? In the end of the day, you might be able to tell whether your signal is astrophysical or cosmological by the amount of variance that you get around the Ellings and Downs. Because, you know, for an astrophysical signal that is dominated maybe by few sources, there's going to be a lot more variance around that curve compared to a perfectly isotropic signal. Now, by that time, you might very well have already identified the hotspots, and so you can say also from the fact that the signal is very directional, you can say that it's unlikely to be cosmological, right? So all these things are different line of evidence that you can put together in order to establish what is the nature of the signal.
Yes, all right, thank you. That was my question.
Okay.
Okay, there is one there.
Dai. Sì. Dai ragazzi, tanto non c'è lezione, non avete niente da fare. Nome?
Ali.
Vai.
I had two curiosities. First is that what is the mechanism that create the supermassive black holes? Because I'm not very sure about that. Like, and also like, when in the history of the universe do they start to shape? Like, in the sense that the only thing that I know is that primordial black hole might seed them, but I don't know how significant is this? Like, is this the leading theory, or are there other?
Okay. Okay, so it is not. Well, it was a very, 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 let's say, exotic possibility up to 10 years ago. Now it's becoming more and more popular because, of course, now that we are seeing a lot of black holes with LIGO Virgo, you know, primordial black holes took a lot of, you know, fly off, essentially. And also because of some JWST results that I can mention in a second. So there are, that's a very good question because the answer, the honest answer is that we don't really know, okay? We have a lot of theories that are kind of natural and they don't rely on primordial black holes. So the idea is that early in the universe, when you start to form the first proto-galaxies, the gas is essentially metal-free. It's hydrogen and helium, mostly. So when you have mostly hydrogen and helium, cooling processes are very inefficient, and so you tend to collapse big clouds of gas. And those big clouds of gas can lead to big stars, and these big stars can end up into relatively big black holes. So depending on the details of these processes, you might, is conceivable to think that in early proto-galaxies, it's relatively easy to form black holes that have hundreds to tens of thousands of solar masses. And this is what we call seed black holes. Then these seed black holes grow by accreting from the surroundings. So in general, the leading mechanism for growth is radiative efficient accretion of gas, right? And then they merge with each other until they grow to become supermassive black holes. Now, this picture is, in theory, it's all fine and beautiful. In practice, of course, it's hard to, first of all, to, well, piece together, and also to reconcile with all the observations that we have. In particular, now we have a lot of interesting observation from JWST that sees a lot of massive black holes very early in the universe. And so, you know, it's gonna stretch a little bit, you know, the growth timescale of these systems. And that's, for example, why, you know, there's a lot of people that think that these black holes are too massive too early to be astrophysical, so they might have a cosmological origin, they might be primordial black holes, some of them at least, okay? There are ways to reconcile this astrophysical seed scenario with the observations, but, you know, we still don't have the complete answer.
The other curiosity was that, let's say that we do the future observation and we have a better understanding of the origin of this stochastic gravitational wave background. And if it is a supermassive black hole background, does it, what questions does it answer? Like, what are we looking for?
Right. So, well, there's a lot of things that you can do with that. So, first of all, the first question that you answer is the supermassive black hole binaries actually do exist and they do merge, which is honestly something that we all theoretically expect to happen, but we have really no observational evidence of it. Okay, and then of course it really depends on how good your observations are. If you're able to see individual sources, if you're able to detect, to identify counterparts, then you can really study the detailed process of evolution of massive black hole binaries in massive galaxies, how accretion works, and all this kind of stuff. You can cross-correlate them. You can cross-correlate the signal with the distribution of galaxies in the universe. You can do all these sort of things, right? Of course, there are different levels of interest here, right? If there are massive black hole binaries, it's great, and we can learn a lot of things about this population. We can gonna build a chart of these binaries in the universe, and it's beautiful. But you know, I'm an astrophysicist, I love this. It's not the most exciting thing in the universe. If it was of cosmological origin, that would be the most exciting thing in the universe. But unfortunately, but you know, if I have to bet my money, I bet on massive black hole binaries, of course.
Thank you very much.
You're welcome. C'è un altro sulla, guarda. Dimmi tu se devo smetterla.
No, possiamo. I think we have
c'è
time for a couple
una
more
mano
questions.
Vado io.
Ok, vado io.
It might be a bit out of topic, but I realized I never asked myself this. Does a supermassive black hole become supermassive because it's at the center of a galaxy, or is there any dynamic that brings it at the center after becoming supermassive?
It's the first thing. So in general, they become supermassive because they are at the center of the galaxies, because that's where anything that happens that destabilizes a galaxy, whether it's that bar instability or its merger or whatever, it funnels a lot of cold gas towards the center. And where the gas goes is dictated by is not really dictated by the black hole, it's dictated by the potential well of the galaxy. So the fact that the massive black hole is in the center, right, makes things such that part of this gas is going to be accreted by the massive black hole. If by any means it was in the outskirts, it would hardly grow anything, okay?
Thank you.
Okay, maybe time for a last question, if there is. Okay, over there.
Last one. Osti, abbiamo perso la batteria. We lost the battery. Puoi urlare.
No, it is just a curiosity. I mean, until now, you are sensible only to the near universe, no? To the low Z. Do you, okay, if you increase sensitivity, you can go farther. So, okay, if you increase sensitivity, you have a lot of more information, but if you can go to higher distances, you expect some change in this noise that you observe in this. I mean, there are maybe regions where there are more.
So the PTA, yeah. All right, so yeah, that's also an interesting question. With the PTA, it's a bit different than, for example, with interferometers, because interferometers, they work in a different way. I mean, they are noise dominated, and then every now and then, boop, you have a signal, right? So the more sensitive you are, the weaker signal that you can see, and you can go farther and farther. So here is a bit different because when we improve our sensitivity, we are just better characterizing this stochastic signal, right? So it's not that we are seeing better this incoherent superposition of waves, but it's generally hard to reconstruct where they come from. One thing that you can do is the following. So if you have a lot of pulsars and you can resolve individual sources, so suppose you have this superposition of signals. The brightest of them, you can actually identify individually and sort of subtract, okay? Now, if you can resolve the nearby ones that are really just located in the most massive galaxies that are in the relatively local universe, then the residual that you get should be correlating with the large-scale structure, okay? And so, if you want to dream, you might be able to do tomography, for example, right? You can actually see how this anisotropy is, right? And you can compare it with the large-scale structure of the universe once you map it with Euclid or whatever else, right, as a function of redshift, to try to understand where the signals come from, okay, and see whether, you know, massive black hole binaries were more popular farther away or close nearby, and so on and so forth. But you need a lot of sensitivity to do that, so I'm not sure that's certainly not going to be in my lifetime, but maybe some of the early young students here. I mean, that's not going to be in my lifetime, and I'm not very old, so.
Okay, so I will stop here. Let me thank Professor Sesana again for this very interesting colloquium.
Thank you.
Thank you to all of you, and I hope to see you for the next colloquium in February. Thank you.